Some corollaries to the theorem that I just proved include these three. Corollary one, if two inscribed angles intercept the same arc, then the angles are congruent. Okay, let's first of all just think about what that says, and then we'll prove that it's true. Here's the arc over here in question, and angle 2 intercepts that arc. Angle 1 also intercepts that arc. The theorem says, or the corollary says, that angle 1 and angle 2 must be congruent. Well, if you just lean on the theorem we just proved a second ago, for instance, suppose I went over here and I said this was a 40-degree arc. The theorem we just talked about a moment ago said that an inscribed angle has a measure that is 1/2 its intercepted arc. So that would make the measure of angle 1 20 degrees. And likewise, measure of angle 2 also intercepts this arc here, so it would also be 20 degrees. The fact is, they both intercept the same arc. They both must be half of whatever that arc is, and therefore they must be congruent. So forget about the 40 degrees. They're congruent regardless of what this measure is, to reach half the measure of that arc. Okay, here's one that pops up and it's sort of surprising. An angle inscribed in a semicircle is a right angle. So we're talking about this angle up here. Angle ABC, and it happens to be 90 degrees. That's what the theorem says, that this angle right here is 90, and it's 90 no matter where I move it here. Notice this number is not changing. Now, why would that be true? Well, a little clue is that it's a corollary. A corollary means that it has to do with the theorem we just proved a minute ago. Think about what has to be true. If this is inscribed in half of a circle, what is the measure of this arc over here? Well, it has to be 180 degrees. So this inscribed angle, the angle ABC, is inscribed in a semicircle, therefore cuts off a 180-degree arc, and its measure must be 1/2 of 180, so it must be 90 degrees. So interestingly, if you inscribe a triangle in a semicircle, it has to be a right triangle. You can imagine why this might come up a lot in the things that we've learned so far. The Pythagorean theorem suddenly comes into play because this is a right triangle. That's a 45, 45, 90. 30, 60, 90 triangles can come into play here. So trigonometry, keep that in mind. That has a way of popping up because it's the way that right triangles can pop into questions about circles. This is an interesting one as well. If a quadrilateral is inscribed in a circle, then its opposite angles are supplementary. Okay, so here, let's talk about what that theorem says first, and then we'll see if we can prove it. It's saying that if you look at the angles of this thing, I'll measure that one. It's about 102. Let's get this one at D. It's about 70, 77. And lastly, let's get this one over here. Okay, we can move this around a little bit, and obviously the numbers will change, at least the ones that are changing when I move that. So whatever moves, all of them are changing right now. The theorem says something a little bit surprising. It says if you add together the angles that are across from one another in this inscribed quadrilateral, then they will be supplementary. In other words, they're going to add to 180. So let's just kind of test to see if this is even true. And then we'll see if we can come up with a reason for why. This one plus this one is exactly 180. And it should come as no surprise that if we add the other ones, 180 as well. Okay, well, I'll drag this around. I think we're going to see that the numbers are changing like crazy, but these aren't changing at all. So what is going on here? Why is this true? Okay, to see what's going on, we need to think about these as inscribed angles. So this angle right here at D, for instance, is an inscribed angle, and it cuts off the arc that runs all the way from E to G, the arc EFG. The angle opposite it happens to be this one, and it cuts off, it's an inscribed angle that cuts off the arc from E all the way to G, but in the other direction. So if we think about this arc all the way from E to G, which is what's cut off by that angle, and then we think about the arc cut off by this angle, which is also from E to G, but the other way, those two angles, the angle at D and the angle at F together, cut off the entire circle. But we know the entire circle's measure is 360, and each of those angles is half of the arc it cuts off, so they must add up to 180. Same with these two. If we look at the angle here, the arc from D to F is cut off. If we look at the angle here, the arc from D to F is cut off. Well, together they cut off the whole circle, 360 degrees. Each is half of the arc that it cuts off, and therefore they will add up to 180. Pretty cool.